we will go to PowerPoint. All right. We are now recording. Hopefully I can't see they don't have an indicator that the sound is okay, but it was. Now, I went to all this trouble to get the this lined up, and now it's, I guess PowerPoint changes some of the parameters. I don't know. So that seems a little better. All right. Now, as I was saying before, I wanted to say this while we're on this. Everything is loaded on Blackboard now as far as I know, and it's all under content. You'll find your syllabus there, the research paper instructions, my locator card, all of the PowerPoints, more than we'll probably get to cover in this class, so I put them all out there. The websites or YouTube videos and other things that other students have sent to me saying they found, or I found myself, that they found these to be useful. And then the YouTube videos that I've done for this class. Now those are all under one click under content, and it's MTH112 YouTube videos. Okay, pretty obvious. Okay, when you click on that, then all the ones for this class will come up. I've arranged them in what they call playlists. I put all the 112 in one playlist, all the 100s in the other, so you're linked to the 112 playlist. Can I get your name, please? James? Okay. All right, let me find you. There you are. Good deal. Anyone else come in since I called roll? Okay. So, any questions? I asked it before, but a few more people have come in. Now, one thing, I don't know if you've noticed this, they came in Thursday afternoon after this class, and all my classes were over with, and resurfaced all these boards, okay? They just put a new sheet of something on. This used to be a chalkboard. It's now a whiteboard, okay? So I haven't tested them to see how they work. Hopefully they erase well and easier and better than the previous ones, but those were well worn. They had been here many years. I'd say well in excess of 10 years. So Blackboard, who knows how long, way before my time. All right. I'm sorry? The desk? Way before my time, too. Now, I've been here 19 years, okay? These same desks pretty much have been in here. I think that desk was brought in from another classroom, the one you're in, but most of these were in this room when I started teaching here 19 years ago. We stick with what tradition. Yeah, no, whatever, I don't know. All right, I had to find some sort of positive, false positive to claim there. Let's get the slideshow set up. I forgot to do that. Well, doesn't seem to want to set up from current slide. All right, and I've also got to do, you can see it, oh, you know you can't, okay. But I've got to change this, sorry. Such a pain in the neck. All right, now we're both on the same screen. All right, I guess we have to go back, and if you recall, find the domain of this function. When you have a discrete function, one that has just individual points, then the domain are the first values. What's in the first is the independent variable. This is dependent. Domain is all the input variables, values. Okay? So sure enough, that was -3, -1, 0, 2, 4. And there they have it, -3, -1, 0, 2, 4. Any questions? Okay? The second of those, let's go back. What's the deal with this one? What do we have to consider? You have a function like this, you assume to begin with all real numbers, because this is a continuous function, unless they indicate otherwise, unless what? Say again? You cannot divide by 0. Exactly. And what would make that denominator 0? x equal negative 5, so you have to exclude that one. And sure enough, that's what they got for b. Excluding the x values that yield 0 in the denominator, the domain of G is a set of all real numbers x, except x is equal to negative 5. To me, it's a lot easier saying set of all real numbers such that x is not equal to negative 5. That says it all too. One thing about this new boards, the glare is even brighter than it used to be, so I'm having trouble reading. All right, let's go back and look at the third one. What was the deal with this one? Any constraints there? Say again? I can't hear. All real numbers is where we usually begin, except this is a physically based question. Volume of a sphere. So, what is your independent variable? R. And can that be all real numbers? Say again?
Can, but not negative.
I cannot be, not even just not negative, can't even be 0. Exactly. How many spheres have you ever seen with a radius of 0? You can't see it because it's not there, okay? Or negative numbers, I can't draw that, okay? Be inside out sphere, I don't know. No. This is a physical constraint on it. It's a sphere, so it has to have a positive radius, okay? So that was that one, and that's what they got here too. Because this function represents the volume of the sphere, the values for the radius must be positive. All real numbers. Now, sure, you can't have an infinite radius sphere unless you maybe are talking about the universe, and we don't know what that is, so we'll let that go. But you can't have anything 0 or less. And then the last one, let's see. How about this one? What do we do with this? Yes, square roots. That's the key here. What about square roots? Second, cannot be negative. Anything inside that radical, as long as it's a square root, cannot be negative. So that's where we begin, and that means what's in there has to be greater than or equal to 0. You can't take the square root of 0. You just can't take the square root of a negative number, and that's what they got here. Oops, sorry, that was still part of C. Here's D. This function is defined only for x values for which the thing inside the radical, 4 minus 3x, is greater than or equal to 0. Well, we solved that inequality, and you conclude, and we did this. Remember what's the key here? When you multiply or divide by negative value, you have to flip the direction of the inequality. These are only for directional inequalities, okay? So that's how this thing, when you divide it by -3, that's what changes from greater than or equal to less than or equal to. And the rest was done, okay? So the domain here is a set of all x's less than or equal to 4/3, 4/3 up here. So it starts at -infinity, goes all the way to 4/3, including 4/3, but cannot go beyond that. And again, on these directional inequalities, what I like to do is pick a value, a pretty simple value, that's in here and outside here to make sure they make sense. One really easy one inside this interval would be 0. If you put 0 in there, sure enough, you can take the square root of 4. That's fine. Pick something outside there. Well, 2 would be outside there, right? If you put 2 in here, 2 times 3x, 3 times 2 would be 6. 4 minus 6 is -2. Can't take the square root of that. So sure enough, that interval appears to be right. An easy little test to do. Okay? Any questions? Okay, was I moving through slides too quickly there? Everybody got it? No one needs to go back? All right. Now, example 7c, note that the domain of the function may be implied by physical context, You can't have balls that have negative radius or even 0 radius. So this one, I think we beat that to death, but they want to beat it a little further. The Jarian's here. All right, good deal. guess everybody labored so much yesterday, they're tired today, and that's a little later getting in. Okay, never mind. Okay, this one, for instance, from this equation, you would have no reason to restrict it. Okay, if this did not tell you it's the volume of a sphere, in fact, if they said y is equal to 4/3 pi x cubed, even though you look at that and say, that looks a lot like the volume of a sphere, if there's nothing to indicate that it was, then it's all real numbers, okay? But, and that's what I said, just the equation alone has no reason to restrict r to positive values, but the fact that it said this was the volume of the sphere, the physical context implies that the sphere cannot have a negative radius, nor can it have a zero radius. Otherwise, it's not much of a sphere. Okay. We beat that, I think, to death. Any questions? All right, now we're ready for applications. That's what we always like to do. Now, again, let me remind you, this author is the very best I've ever seen. To every time he gives an example, I think just about every time he gives an example, he then gives a checkpoint right below it that has very similar but different kinds of exercises in them, okay, examples, and you're asked to do those. And here's Shun. Okay. I know you're in here. There you are. Okay. All right. And so those checkpoints, the good thing about here is I've seen other books that have those, something like they don't call them checkpoints, but he provides audio-video solutions for these checkpoints at larsonprecalculus.com. He has a website. You don't have to pay anything. All you have to do is go to it, okay? Now, the strange thing is then his odd number exercises at the end of every section. They're at a different website, but again, he has them there, and that's at calccheck.com. So he has two active websites that you can go to and get additional help. And if you're struggling with any of this, my suggestion to you was as soon as you get out of class, and if you don't have another class, or if you're going straight home or something, whenever you can, as soon as you can, try to do the checkpoints at least, because then you can go to that. And then do your homework, and do it while it's fresh in your mind. I've had so many students say to me over the years, 19 plus years now, oh, I knew it when you were talking about it in class, but when I got home, I couldn't remember how we did it. Well, that's one reason I record, but it's also a reason that I suggest you do things as soon as you can after class. If it's a little fuzzy, practice them as soon after class while it's all fresh on your mind. Get off my soapbox here. Let's go on to application. All right. We didn't start this, did we? Okay. It seemed like we had done one like this, but maybe not. You work in the marketing department for a soft drink company, and you're experimenting with a new can for iced tea that is slightly narrower and taller than the standard can. For your experimental can, here's the key here, the ratio of the height to the radius is 4. Time out right there. When you're doing a problem like that and you're given that piece of information or something like that, I like to stop right there and write that down mathematically. In fact, word problems are first step. Translate the words into algebra, right? Now you translate this statement for me right here. Ratio. What does ratio mean? What does ratio mean? Did someone say something? I heard a few mumbles, but I couldn't make them out. What does ratio mean? Okay, it has to do with an equation. A ratio is a comparison of two numbers. In what kind of sense? One of your 4 basic operations. Addition, subtraction, multiplication, or division. What's a ratio? Division. In the division sense. The ratio of the height to the radius. Now, how would we express that mathematically? Ratio of height to radius. Let's see, I've got to get my pen activated, and I'll do that this way. Okay, height divided by radius, that's the ratio of height to radius, is, how do you translate that? Equal to 4, I can translate that. There we have it. There's an equation that states the same thing they do here. The ratio of height to the radius is 4. Now they get to telling you what, oh yeah, and by the way, I chose H for height and R for radius. Was that okay? You could have done X and Y. You could have done anything. The other reason I did this, here's the picture, and this is the first thing I would have you do is draw a picture. Now, you don't have to have it that fancy with iced tea and lemon and all that kind of stuff. All you need is a representation, okay? And what a new can for iced tea, these cans are just about always right circular cylinders. Now, what do we mean by that? Let's start with the circular part. The base of this, which including the top of this, in fact, every cross-section of this is a circle, okay? Now, right means it's right angle. The base is right angle to the side, okay? Not too many soft drink cans they have that lean, okay? They would be weird to drink, okay? So they don't do those. They put them all right circular cylinders, okay? So they drew the picture for us, and they labeled the radius is from the center of that circle, or the one down here, doesn't matter, or any cross-section, to the outer limit there is R. And that could have been in any position there. That's always R. And this is the height, and the ratio of the height to the radius is 4. Okay? Now it says, write the volume of the can as a function of the radius R. Oh, we got to figure out what the volume is, don't we? What is the volume of a right circular cylinder? Let's call V volume, okay? Now, anytime you have a right regular shape, the volume is pretty easy. What I mean by right regular shape, right is meaning it's perpendicular to the base. This is. Regular means whatever the shape is at the bottom is the shape all the way up. That's regular, okay? And the shape at the bottom is a circle. So, what is the volume of every right regular object? Okay, if you were talking about the volume of this room, how would you describe it? How would you calculate it? Okay, you're close. That's not of the room, but of this thing. Okay? The room. Let's stick with the room. Let's just imagine you didn't have these little indentations in the room, and this was just a rectangular room here. Okay? What would be the volume of this room? The what? That would give you the area of the floor or the ceiling or any cross-sectional area times the height. Exactly. So you just got it. The area of the base times the height. Anytime you have a right regular object, then it's the area of the base times the height. And what's the area of this base? What's the area of that? What did you say that base was? A circle. What is the area of a circle? Yes, pi times radius squared, pi r squared, okay? So the volume of the base is the area of the base times the height. The area of the base is pi r squared times the height, okay? Diana? Okay. All right, good deal. Okay. Now, we almost have it right there. We have the volume as a function of both the radius and the height. We want it as just a function of the radius. How can we get that? What's the thing in our way from having this be volume of radius alone? H, exactly. If we could get this H expressed in terms of R, we would have the problem knocked, wouldn't we? Okay, now how can we do that? Use that constraint. Let's solve this for H. And what would that, how would we do that? Second? Second, multiply both sides by the radius. Because here, that will wipe out the r, and that gives you h equal 4r, right? Okay, now down here, instead of h, we'll put v is equal to pi r squared times, what is h? 4r. Okay, now just clean it up a little bit, bring the 4 out front. 4 pi r squared times r is r cubed. There we have volume as a function of the radius. Now this is this particular can that happens to have that ratio. Oh, and there they wrote the ratio too, didn't they? Shame on them, they should have let us write it. Okay? There we've done it. Right, the volume of the can is a function of the radius alone. What if they ask you to write the volume of the can as a function of the height alone? Say again? Yes, we go back to this one and solve for r. Now what I'm going to do, because I'm running out of room, I think what I'll do is, you give me your favorite color other than black. Purple, okay. All right. We'll start with what we have here. H is equal to 4r. Now solve that equation for r rather than for h. So how would we do that? Divide both sides by 4. Here the 4 goes away and you have r is equal to h over 4. Then you go back to our original equation that we figured out. V is equal to pi r squared h. And instead of the r, we put in h over 4. So that would be pi. Instead of r, we put h over 4. That's what r is, right? But we've got to square that and then multiply by h. I'm running out of room, okay? So let's, what should please excuse my dear Aunt Sally tells you to do first? The exponent, square first. Oh yeah, parentheses. And what's in the parentheses is just a division. Okay, got it. And then we do the exponent, okay? So that would be, I'm going to come up here, v is equal to pi, and what's h over 4 squared? Help me. H squared, is that what I heard mumbled? Over 16, and then times h. Okay, let's get it in sort of a final form. Let's go to all the constants out front. I would call that pi over 16, right? Pi 16ths. Then h squared times h is h cubed. There we have it. The volume is pi over 16 times h cubed. Now, frankly to me, this would be the easier way to measure the volume of the can. It's really easy to take a ruler and measure how high the can is. Then you take that, multiply it by pi or 3.14 or whatever you want to do it, divide that by 16, there it is, and then cube that height. You've got the volume of the can every time. This is a much simpler formula. You don't have to divide, just multiply, but what's the problem with that? Determining that radius. Do you know where the center of that can is? Not an easy thing to find, okay? So to find the radius is not that easy. Now, maybe you could say diameter rather than radius, and that's still not that easy because you could do all sorts of things there and get different measures. The maximum distance across here would be your diameter, divide that by 2 to get the radius. But shoot, just take the height of the can, use that formula, you got it. Really easy. All right, any questions? Does this make sense? Beat it to death? Okay, let's see. Here's what they do first. That V of R is equal to pi, well, this isn't quite true, okay? Volume is equal to pi R squared H. That volume is a function, that's V. It's not as a function of R. This is a function of R and H. We want it as a function of R, okay? We want this alone. This has an H in it, so this is not technically a function of H of R alone. It's a function of H and R. Okay? So we use our ratio to find out that H is equal to 4R, just like we did before. Now this is a function of R alone. But we can clean it up a little bit. Multiply the 4 times the pi. Those are your constants out front. And then R cubed is there. That now is V as a function of R. Okay? The second one, we start with the same formula. The volume hasn't changed, but we want this as a function of H. This is not as a function of H alone. This is R and H. Okay, just like this was R and H. But now we'll use H is equal to R over 4. I mean, 4, let's say R over 4. I'm sorry. R is equal to H over 4. You know, I'm saying it wrong. And put that in for the R squared, but now you have to square the whole thing, H over 4 squared, which would be H squared over 16, which would be pi H cubed over 16. Now, we wrote it slightly differently. Either of these would be fine. This is one reason I really don't care for WebAssign and those automated packages. If you were doing this problem and they were looking for that answer, but you said pi over 16 times H cubed, guess what it would tell you? Wrong! And it's not wrong. It's absolutely correct. So it turns out that half the time you're trying to figure out what form do they want the answer in. And if you only have 2 or 3 tries, you might try 2 or 3 absolutely correct ones and they still say it's wrong. That is a pain in the neck to me. So that's why I sort of avoid those. But if you like to use them, I can get it set up for you. But shoot, with these calccheck.com and larsonprecalculus.com, wow, you have all the, to me it seems like you have all the assistance you need. But if not, I can get you so you can access WebAssign. Do any of you particularly want that? I'll be glad to do it if you want it. Okay. What's that? No, I'll just give you that so you can do anything you want to on it. I'll put them all out there and you can do whatever you want to on it. You would want to have that? Okay, I won't make any specific assignments. I'll just put the whole package out there and you can use it if you want to. Huh?
That's fine. Like, I would love to have the extra reference. That's what you're saying.
You would want to have that in addition to this.
Like the reference to learn how to do this.
Okay. All righty. Well, then I will do it now. You will have to have a new book. You know that?
I understand. I just don't have a book at all. So
right.
That's why I'm wondering.
Okay. Because you have to buy a new book, as far as I know. Maybe you can buy WebAssign separately in the bookstore. I guess you can. But they say that it costs as much as a new book. Okay. All right, we got down to the brass tacks here. Okay, yeah. Yeah, no, they charge out the ears. I mean, they charge for WebAssign. Okay. Here's what they do. I mean, WebAssign, basically, what they tell us, oh, no, we provide that for free. But they make you buy the new book to get WebAssign. They charge you this much for the new book. They say, well, the student already has a book. Can he just buy WebAssign? Oh, yeah, well, now it's $75. Okay. Well, why was it free before and $75 now? Because they want their money. Okay. Show me the money, they say. Okay, no, they didn't really say that. But. All right. Does anyone want it? Who's already got a book? I'll be glad to activate it if you need it. If you find it useful. No. Okay. If you do, let me know. If only one person needs it, I'll do it. I mean, it's no skin off my nose, I hope. All right. They skipped the next example, which was example 9. Okay. Let's do that. All right. What I have to do is go to screen, white screen. Okay. I'll write this out because some of you don't have your books. A batter. Oh, let's go back to black. All right. A batter. Okay. A batter hits a baseball. Okay. At a point I abbreviate it like crazy, 3 feet above the ground, okay, at a velocity of 100 feet per second. Sorry, running out of room. Can you read it kind of? Okay. And at an angle. What's that? Okay. Which, that's just at the very end?
Oh, like I can't understand that.
Okay. Well, listen to me and write it down as I speak. A batter hits a baseball at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. That's my shorthand, okay? The path of the baseball, I'm just going to say the ball, has already identified it as a baseball, is given by this function. I don't like the way they named it. F of x is equal to negative 0.0032 x squared plus x plus 3. Okay? Where F is the height of the baseball. So why didn't they call it H? Okay? Height of the baseball in feet. Okay? And x is the horizontal distance, okay, from home plate. From home plate. Okay? Second? I can't hear. Oh. Well, I didn't particularly, but I guess it did. Where did it go? Let me try this first. Why did it do that? Okay, let's try that. Control what? Z. Okay, let's get this off. Control Z. That does nothing for me. Okay, good try. I mean, I'll
It works on Microsoft.
Okay.
And you press Control Z, it goes
Well,
back as many times as you want.
evidently, I did too many things in between.
I don't think he's on the Microsoft program.
What's that?
He's not on the Microsoft program, are you on PowerPoint?
I'm on PowerPoint, and that's Microsoft. But it just does these things sometime. I hate it. Okay.
See all slides.
Say again.
Go to see all slides.
Again.
See all slides.
See our slides. See all slides. Where do you see that one? Right here. But you see, not the one I did. Okay. All right. Sorry about this. I don't seem to be able. Let me try it here. What did you say? Control Z from here? No, that just goes back one.
Hey, it did go back.
Huh? Okay, I'll try it again. Control Z, Control Z, Control Z. Nothing. Okay. So let's go back to screen, white screen, and then do Control. Let's see. What was the other one we tried? Previous. Let's see if that works here. No. I think too many clicks got in the way there. Okay. What's that? That button down there?
No, just just to make the options pop up. Like the,
Oh, okay.
okay, now click on the screen.
Screen.
Okay, what is it? Main show, hide, 8 markup.
Let's try it.
So what do you vote? And show or hide.
Yeah. Try it again. It's Gone but not forgotten. Okay, right? I don't want to write all that down again. Is that okay? Please say yes. Okay. All right. Let's start where we would have it. Here's the important part. The function. F of x is equal to negative 0.0032 x squared plus x plus 3. Okay? Where F is the height and x is the horizontal distance from home plate. Okay? Now, the other things that we had, he hit the ball, and by the way, what would you do first on problems like this? Especially if they didn't do it for you? Say again? Okay, even before that. Okay, someone may have said, I heard some mumbling, I can't make it out. There were thousands of words. Say again? Draw a picture. Draw a picture. Always draw a picture if you possibly can. So they don't have to be pretty pictures. They can be really ugly pictures like mine. Here's a baseball player. Here's the bat in his hand. Okay, boy, big bat. Okay, and he's going to hit the ball where? Where's he going to hit it? 3 feet above the ground. Isn't that about normal? Unless you batters? Okay. Yeah, right about there. Sweet spot, right there, about 3 feet above the ground. Right? Okay. Hit the ball about 3 feet above the ground. And he's going to hit it with a velocity of 100 feet per second. Okay? This is the initial velocity of that ball. You don't see that in the problem per se, except I'm going to explain something to you. Notice what all your dimensions are. Height in feet. Okay? It's an important thing here that, and this is the horizontal distance in feet from home plate. Your velocity of feet per second, 3 feet above the ground, everything in terms of feet. So, does anyone know where this 32 comes from? Okay. Say again? Okay. We're thinking accelerations. We have velocity, we have displacement, acceleration. Any say again? Acceleration due to, what did you say?
Said how fast the ball was traveling.
No, that was 100 feet per second. Did you say something else? Acceleration due to gravity. Right? Anyone know what it is in the U.S. customary system, feet system? 32 feet per second squared. So here's where that 32 came from. But why in the world do we have two decimals in front of it? Remember, what goes, this is displacement, this is velocity, this is acceleration. Acceleration 32, velocity should be 100. But what they sort of done is divide that by this and then you square it. That's where your 4 decimal places come from. You don't need to know all this, I'm just explaining it to you. It's a weird thing, but this is exactly where that came from. So he's going to hit that ball with his big old bat there, and hopefully he's at home plate here. Here's his home plate, sort of an ugly home plate, something like that. Really ugly home plate. And out here somewhere is a fence, okay? And this fence is 10 feet tall, okay? Now the question is, oh, and the distance from home plate to the fence, obviously I'm not drawn to scale here, is 300 feet. Okay, so this would be what, probably right or left field corner. That's usually 300. Out there is longer than that, okay? I don't know, I'm making this up. Okay, now, that's what the problem says. All right, the question is, we're given where he, well, yeah, I hit it 3 feet, that's in the problem, 100 feet per second, and at an angle of 45 degrees. That's the one thing we don't have here. He hits that ball, and when he swings that big old bat, hits the ball, it goes at an angle of 45 degrees. Okay? That's its initial angle. This is the equation that describes that. Okay? Will the ball clear a 10-foot fence located 300 feet from home plate? Well, guess what? The horizontal distance from home plate, that's this, 300 feet, right? This is the height of the ball at any point. Here it's 3 feet, because guess what? At 0 distance from home plate, when the ball is right over home plate, how tall is it? 0, 0, 3 feet. Yeah, that's where he hit it. 3 feet right above home plate. Okay? Now, I didn't quite draw that right either, but it's close enough. Okay. So, what do we do? What do you do with Glade? Plug it in, okay? And what does that give you? Your x is the horizontal distance from home plate, so let's do it. F of x, which is the height of the ball at any point x, including 300 feet from home plate, that's equal to negative 0.0032. And then what do we do with the x? Say again? 300 feet squared. I'm leaving out the units for now. Plus 300 plus 3. Okay? Let's see what that turns out to be. You might need your calculators or not. Let's see. What's 300 squared? Anyone know? 90000. You double the number of zeros, so you're absolutely right. 90,000 plus 300 plus 3. Okay? Now, multiplying those two together, that's going to give us a negative. And these 4 zeros here are going to wipe out these 4 zeros there. Move 1 decimal 4 places one way, one the other. You just have 9 by 32, right? 9 by 2 is 18. Carry the 1, 28. That's negative 288 plus 303. What does that give? More like 15. Right? All right. 15 feet. Okay. There it did it again. Now why? I do not know. Let's see. Let's try what you said before. Control Z. Nothing happens. Huh? What happened? Okay. Okay. All right. But what we wound up with 15, right? 15 feet. That's going to more than clear the 10-foot fence. Even with that right fielder climbing the fence as high as he can, I don't think he's going to get up 15 feet, will he? You can? Okay, okay. Oh, okay. You've seen 15 feet? Huh? Yeah, if he's really climbing the fence, he can get some extra levity there, but boy, 15 pretty hard to do. Okay, if it was 10, yeah, I've seen him do that. 10-foot arms fan. He should be playing basketball. He should be playing baseball. Okay? Put him on the court. I want him as my center. Okay? Okay. He should be playing basketball. If he can jump 15 feet, he can dunk it from his waist, you know. Of course. Okay. All right. We'll take your word for it. So we got 15. Yes, it should clear the 10-foot fence. All right. Let's move on to, here's another one. Example. Here's what I'm not sure what's happening. This is just a real big pain in the neck. Okay. Let's try it again. Y'all really need your book on this one because I can't do it. The number V, okay, in thousands of alternative fuel vehicles I'm going to call these AFVs, alternative fuel vehicles, okay? In the U.S., I should write United States, so I'm putting U.S., I'll abbreviate like crazy, increased in a linear pattern from 2003 to 2005. That's ugly, okay? From 2003 to 2005. In other words, 3 years, okay? 3, 4, and 5, okay? Then increased in a different linear pattern, okay, from 2006 to 2009. Okay, 4 years, 6, 7, 8, and 9. Okay, as shown in the bar graph. Now, some of you have your books, you can see it. Some that don't, I'm going to hold mine up in just a minute. These two patterns can be approximated by the function, since they're two different patterns. This is number of, and why they call it vehicles, I guess, okay, number of vehicles as a function of time. That time will be in years, not seconds, minutes, or hours, but in years, is going to follow. This is a piecewise defined function because it's one thing for the first 3 years, a different thing for the next 4 years. So here's how we express it. 29.05 t plus 447, they're giving you this, I'm not making it up, okay, 0.7, okay, and this is good from 3 less than or equal to t less than or equal to 5, okay, and then it's 65.50 t plus 241.9, and that's from 6 less than or equal to t less than or equal to 9. Okay? Now, all right. Here's a picture for those who don't have the books. Is it better if I do this? You see, for the first 3 years, 2003 to 2005, is sort of a gradual slope. Increasing, but gradual. But then after that, it went up much more steeply. Now that's a different straight line linear approximation. Not exact, but an approximation, but it has a different slope. Here's the slope for the first 3. It increased 29.05 thousand, because this is in thousands, of vehicles per year. Here it went up to an increase of 65.50 thousandths. Okay, so that, in other words, would be 29,050 would be increase per year, 65,500 increase per year. That's what that's telling. This thing over here, that's not telling you much at all. Okay? Yeah, you might say that's the y-intercept. The y-intercept when t is equal to 0, right? These t's are never equal to 0, so don't try to extrapolate back there. They're no good back there. It's only good in between these values. Now notice the other thing they've done here, and this is a pretty typical thing. Rather than writing 2005 and 2003 and 2006 and 2009, they just dropped this part and did from, t is the year from 2000, 3 to 5 and 6 to 9. Okay? So in other words, if you did try to extrapolate back, this would be giving you the number when t was 0. That would have been this number in year 2000. We don't know that, okay? And we don't even care about it. This is only good in that. This is a designated domain. You can't extrapolate back here or here. Obviously not here because it takes on a different slope there, okay? And you can't really do much beyond year 9 either. Okay. Now, use this function right here, v of t, to approximate the number of alternative fuel vehicles for each year from 2003 through 2009. This is what I call busy work, okay? But let's pick a year. Pick a year between 2003 and 2009. I don't care which, pick a year. 2007 and 4, I heard 2, didn't I? Okay, we'll do them both, okay? Let's do 2004 first. How would we determine the number of vehicles in 2004? Okay, what will I plug in? V of 4 would equal to, which one do I use? The top one, because 4 is in between 3 and 5. So that would be 29.05 times 4 plus 447.7. You got calculators, hopefully? Plug it in, plug it in. See what you get. Or do it in your head. That hard, but it's tedious. That would be a 0, a 2, a 6, and 11 plus that. I hope I did. Oh, wait, I forgot my decimal. Okay, oops. 116.2. Help yourself. Okay, that would be 563.9. Is that what y'all got? How many vehicles does that represent? $563,900 vehicles. You think that's going to be exactly true? No, it's just representing that. This is an approximation, okay? But around 564,000. Let's see what they got for t equal 4. 563.9 thousand. They left off the 1,000 part, but that's what they should have. Okay, the other one you said was 7?
It don't matter. I said 7.
7? Is that what you said? Let's try it for 7. Okay. B of 7. How are we going to do that? Plug it in to what? The second equation, because 7's in between 6 and 9. Okay? So that'll be 65.50 times 7 plus 241.9. Can do this, not in my head, but on the paper here. Y'all see if you can get it done first, okay? 0, 5, carry a 3, 8, carry a 3, 45, plus, is that 247.7? I can't even read my writing. 240, no, 1.9. I'm reading the wrong one. And that would be how much? 7? No, it isn't, is it? Yeah. 700.40. Is that right? Yeah, it is. Okay. Which would be how many vehicles? 700,400 approximately. Okay. Vehicles in 2007. You see how to work that? Y'all want to do every year, don't you? Go home and do it. Okay. All right. Not going to take class time to do every one, but you can see how to do it. This is piecewise defined functions. Okay. And it seems to be pretty good. Warning though, don't try to extrapolate beyond what your domain is. Those functions are only good within those boundaries. Okay. Now we are finally ready for difference questions. Okay, now what I'm going to do here is, let's see, erase all ink on slide. No, it won't do it here. Who cares? What I have to do now, believe it or not, is unwhite a screen and go back to this. Strange. Okay. Let's talk next about, sorry. Every time I did a previous slide before, it went back a slide. Okay. Difference quotients. What does that term mean to you? Anything?
The difference in dividing.
Okay, quotients mean dividing and difference mean subtracting. So somehow you're subtracting and dividing here, right? How are we doing that? Let's see. One of the basic definitions in calculus employs this ratio. Okay? F of x plus h minus f of x divided by h. Okay? Where h cannot, of course, equal 0. From what planet? No, I mean, does that make a lot of sense to you? I see partly a yes and partly a no there, okay?
H can't equal 0 because it's in the denominator.
It's in the denominator, you're absolutely right. Now, guess what? Y'all have seen this before, whether you realize it or not. What does that look a little bit like? A slope equation. Excellent. What is a slope equation? Now, you answer me this. What does f of x stand for? Y. Okay? There's a y. This may have been a y1. y1 minus y, or y2 minus y1. There's a difference. Now, where are your x's in this? Here and here. And what is this x? x2 minus that x, x1. What is x plus h minus x? H, you got it. This is a slope formula. Change of y over change of x. That's nothing new. We've had that before. It just changed the way it looked, right? This is a difference push. Difference here, difference here. Take this, subtract it here. You got h. This is a change of y's. Take a quotient of them, and you've got the slope. So it's not really all that new. It's called a difference quotient. Okay? Oh, here we have it. I thought they didn't write this down. So this is what I just wrote. That's called the difference quotient and illustrated in example 11. So let's go to 11. Okay, here we have it. Here's your f of x. X squared minus 4x plus 7. Find the difference quotient. Now, what you reckon we're going to have to find first before we can plug it in? Second, we need to find what this thing is, f of x plus h. So how do we do that? Plug it in, plug it in. So how do you do that? X plus, wait, do it one step at a time. X plus h squared minus 4 times x plus h plus 7. Right? Now let's do that. What's x plus h squared? Anyone know? Say that again. I hear. Okay. Okay, I heard it. X squared plus h squared. Everybody agree with that? Huh? Yes. Oh, shame on you. Yeah. You're leading them astray. Okay. Shame on you. Okay. Say again? Okay. Yeah, you got an xh in there. What does it mean to square an entity? Multiply it by itself. So that would be the same. X plus h squared. I can't write. Goodness gracious. That's so ugly. Okay. Yuck. I love this program. It's so handy. I just need to make no errors. All right. That would be the same as what? X plus h times x plus h. Now that's multiplying two binomials. What's our favorite way to do that? FOIL it. Okay, and what does that give you? X squared plus xh plus xh plus h squared. And what do you have? A smiley face, right? Okay. Never mind. Okay. What does this give you? X squared plus what? 2xh plus h squared. So did you give me the right answer before? No, you left off the 2xh, okay? Now you can write it out here. I don't care where you write it. But usually we do it in between. Now, can I give you the shorthand for this? Every time you square a binomial, that's what you're going to get. So can I give you a shortcut? Square the first, you did it, but now do twice the product of the two, plus 2xh, then square the second. That gives it to you every time. And that's exactly what we did. Square the first, twice the product, and square the last. Okay? Or you can write it out every time in form. Okay? Whichever, but don't give me x squared plus h squared because it's not it. Okay. Next. Minus 4x minus 4h, I used to be in that, plus 7. Okay? And unfortunately, that's what f of x plus h is. So now we can go back and do our difference quotient. The f of x plus h is this, x squared plus 2xh plus h squared minus 4x minus 4h plus 7. Minus, now what's your f of x? There it is, right? So put that in your parentheses, because when you're subtracting, put them in parentheses. X squared minus 4x plus 7. And then we take that thing and divide it by h. Oh, that looks like so much fun, doesn't it? Okay. Except, let's clear that parentheses and see what you got. X squared plus 2xh plus h squared minus 4x minus 4h plus 7. And then distribute that minus sign, and what does that give you? Minus x squared plus 4x minus 7. Everybody see that? Divided by h. It doesn't look a lot better, but a little bit. But now what can we do? Simplify. How can you simplify that? Here's an x squared. There's a minus x squared. They add to 0. Anything else? Minus 4x plus 4x. That adds to 0. Plus 7 minus 7. That adds to 0. What do we have left? We have 2xh. Okay. I don't know what it's doing. Okay. Plus h squared minus 4h divided by h. Now what can we do? That numerator especially. What do you notice it has? A what? It has an h squared. I see that. What does every term have? Yes, someone said factor out an h. Okay. This gives me factor out h in the numerator. What you have left? 2x plus h minus 4. Divide that by h. And now what can we do? The h's divide away. So what's your difference quotient? 2x plus h minus 4. That's pretty simple, isn't it? Did it ever look like it was going to turn out that simple? Okay. Guess what you do? How do you eat a 5,000-pound elephant? One bite at a time. So the same thing in these problems. They look pretty complicated. Just do it a bite at a time. First, figure out what your f of x plus h is. That's here. Hopefully it won't take as long as we did that time. Subtract off your f of x, which they already gave you. Divide that by h. Write it out. Simplify. You'll get it done. Let me give you a few homework exercises. I know you don't want to go home with nothing. Any of the odds 5, either 5 or 7. Do 9. Any of the odds 11 through 19. any of the odds 21 through 31, either 33 or 35, any of the odds 37 to 43, either 45 or 47, any of the odds 49 to 59, and then you can do your choice, odds 61 through, wow, 75, I guess it is. And then start trying some of these difference quotients, 77 to 83. Okay? We'll come and finish wrap up those others later. What's that?
Is there any on, there's some on page 46.
This goes on to page 47 and 48. You need pictures? What's that? Okay. You had the first part of those before, right? Okay. Let's start with the new ones that we didn't have before. Okay. Now I said 37 to 43, then 45 or 47. I gave you those before, and I think I gave you 49 through 59 before too. So the
Giving us all odds.
Yeah.
Through 77.
Well, not all, but in groups. In groups. Then the new ones were 61 through 75, any of those odds, and then try 77 to 83. All right. Good deal. Sorry we ran over, but no extra charge. Okay. All right. Let me.